flood basalts. Okay, how do flood basalts erupt onto the surface? We end up having either a thick dike that creates large volume flows, or we can have a thin dike that will give us smaller volume flows. An example of this is the Columbia Plateau. It consists of a thick sequence of basalt flows, about 15 million years old. They're fed by dikes, including one shown by a black line there on the southeast corner there of Washington. Some flows are large volume and very extensive, including one that covered most of the area there shown in pink, so covering well across the state line as one lava flow covering that entire area is very large. Okay, so these are very big features. Picking back up on flood basalts, the next question in your notes is, where does the magma from a flood basalt originate? So starting with this slide, the origins of flood basalts. First we have a plume rising through the mantle. Anytime we're talking about a mantle plume, we're talking about very hot rocks in the mantle, mostly solid when they're deep in the mantle because of the pressure that they're under. So we have a rising mantle plume that is probably mostly solid deep in the mantle. Next, that plume spreads out at the base of the lithosphere. Remember, because the difference between the asthenosphere below, where it is hot and weak, and the lithosphere above, the lithosphere is cooler, it's more solid, it's rocky. So when this hot material hits that cooler, more brittle area, it spreads out along the base of it. Then we get decompression melting that melts the plume, which in turn melts the adjacent asthenosphere or lithosphere. Okay, so at this, the fissure opens up, it releases pressure, and as a result of that released pressure, we get decompressional melting. The rocks that are there are able to melt at a lower temperature than they normally would be able to because of the released pressure. Okay, and that results in our flood basalt. This map is showing us where we find flood basalt. So these are not currently active, but rather these are old deposits. So we're looking at the Columbia Plateau here. It's probably related to a hot spot, the one that is now below Yellowstone. And this was erupting 15 million years ago. The next one is in the North Atlantic, around Greenland and Scotland. This formed above a hot spot that is now beneath Iceland. The next one is in India. These are the Deccan Tramps, erupted at the same time as the extinction of most of the dinosaurs 65 million years ago. So it's thought that there was a combination between this increase in volcanic activity, a major meteor impact, and the death of the dinosaurs. The next one is in Siberia. This erupted at the same time as a major extinction event that is called the Great Dying 250 million years ago. So as you can see here, two of the largest extinction events in the Earth's very long history are linked to these flood basalts. It's pretty interesting. South America, some flood basalts are on land and some of them are offshore, probably formed when the continent was over a hot spot. The next one is Afar. That one is accompanied by modern rifting at the junction of the Red Sea, the Gulf of Aden, and the East African Rift. So where that area is breaking apart, is diverging, we have a flood basalt deposit. Kerguelen, basaltic eruptions that are related to a hotspot, and Ontong Java is the largest oceanic plateau, uh, and it formed over an oceanic hotspot. Okay, so as you can see, there's a connection between uh, being on a hotspot and having a large flood basalt deposit, because it is that mafic, very hot mantle material working its way up to the surface and then just going crazy, just flowing with a low viscosity covering a large area. What are the hazards of basaltic eruptions? So we've already seen some videos of lava fountains, of a eruption column of lava flow, but taking a look at them not just as interesting to look at, but what are their actual hazards. One thing I want you to think about is, does this hazard just affect the area immediately around the vent, or can it extend farther away? So our first is the lava fountain on the left. Most material falls back near the vent, so this, if you were standing right next to it, would be horrible because it's throwing molten rocks up into the air, but it's pretty easy to stand far enough back that it's not going to affect you. The next one is volcanic ash. It can reach heights of several kilometers and impact areas very far downwind. So this one can affect far beyond just around the vent. Lava-caused fire. Flammable structures and vegetation may be burned by lava flow. And so that can spread far beyond the vent as well. Lava flow. This changes the landscape and it makes certain areas uninhabitable. So in this image, showing you a lava flow that's just moved down a city street. So that street is gone. It's not that you can go through and sweep it out like you might ash. It's solid rock right there now, filling the entire street. So that street is gone. Other hazards with basaltic eruptions. If we get an eruption near an ice sheet or snowy volcanoes, that can melt the ice and cause huge floods. This image is showing us an area in Iceland, and there are half a dozen basaltic volcanoes beneath this ice sheet that's pictured here. So, forget about climate change. Just if these volcanoes go off and melt this ice sheet, it could contribute pretty significantly to sea level rise. Okay. Also, gas hazards. Gas hazards include sulfur dioxide combining with water to form sulfuric acid, possibly affecting climate. In the bottom right photo, this is of Laki, Iceland, where just such a thing has happened. And when you have sulfuric acid in the atmosphere, this is what we call acid rain. And so this can affect all sorts of things. Usually it's not a very strong acid, but it's strong enough that it could irritate your skin, that it could start dissolving certain types of rocks that react with acid, like limestone and marble or travertine. Things that people like to build gravestones and statues out of are very easily worn down by acid rain. So as we get more sulfur in the atmosphere from volcanoes or from coal plants, for instance, that increases the incidence of acid rain. All right, what are composite volcanoes? What are the characteristics of a composite volcano? The first one is the eruption column. Okay, that's this area that just shoots ash very high up into the atmosphere. So the eruption column has tephra, that's T-E-P-H-R-A. That's this rocky, ashy material similar to pumice. So tephra and gas rise high into the atmosphere. Tephra settles around the volcano, and ash can drift long distances. So once it hits a certain point in the atmosphere, it's sort of smooth sailing. It can, if it's a large enough eruption column, it can actually spread ash around the entire planet. And that has some pretty big, brain freeze there, implications for global climate as well. If we have ash going all the way around the planet, that dims the amount of sunlight coming in, and that changes everything, temporarily anyway. The next is pyroclastic flows. These are violent eruptions of hot gases, ash, and angular rock fragments. These move extremely fast, hundreds of miles per hour, and it's just a nightmare coming down a very steep slope, so you do not want to be near one when it is occurring. The next one is lava flows and domes. These can erupt from a summit of a volcano or along the flanks, along the sides. This is from moderate to high viscosity, so they move slowly. And the viscous lava breaks into blocks. So this can be a hazard as pieces of the block, pieces of the dome break off and fall downhill. It can trigger a pyroclastic flow. Landslides and mud flows. A volcanic mud flow is called a lahar, L-A-H-A-R. And they occur when large volcanoes that have snow and rain at the summit erupt and melt all of the snow at the top. When the volcano erupts, the snow melts, causing a mud flow called a lahar. Steep slopes, loose rocks, and loose ash contribute to hazards of mud flows. So these can come down, and once it is mixed with water, they act like cement when they are deposited, when they finally get to where they're heading. And what type of rocks form from composite volcanoes? So these are going to be intermediate to felsic rocks. Okay, what type of rocks form from composite volcanoes? Intermediate to felsic rocks. Okay, and remember we're talking about the composition there, so that means we have a higher silica content. That's why there's such explosive, dangerous eruptions at a composite volcano. All right, looking at the different rock types that are there. The first one, we have various types of ash, lava, and mud flows. Various types of ash, lava, and mud flows. The next one is andesite. Remember, that's the extrusive igneous rock that forms from an intermediate volcano. Right, throwing a lot of terms at you. And this is how you need to be able to understand what I'm talking about. Right, putting all of these things together. So that image with 3 different volcanoes, with the intrusive rocks formed from the magma and the extrusive rocks formed from the eruption, would be really helpful for you to study on maybe flashcards so that you can remember this stuff. So we get andesite, we get tephra from the eruption column. So again, this is the really ashy material, and it can end up getting what's called welded, where it's so hot when it settles that it welds itself together. Tuff is the name for the very fine material in pyroclastic flows. So tuff from pyroclastic flows, and mud flow deposits. So if you take a look at the scale here with this man standing on that mud flow deposit, that goes well above his head and well below his feet. This is a very thick deposit. So you can see just the scale of this hazard. If that much mud is coming down off of a very steep slope at a high speed, you want to be out of the way. Some famous composite volcanoes before we talk about the disasters that are associated with composites. We've got Mount Fuji. It last erupted in 1708, and it occurs because of a subduction zone off the coast of Japan. The next is Mount Kilimanjaro. It is the highest mountain in Africa, and its formation is related to the East African Rift. The next image is of Mount Etna. It's on the island of Sicily, and it's in a very complicated plate tectonic setting. Okay, here's a night shot of Mount Etna erupting. This is a good one to YouTube. There are all sorts of great videos of Mount Etna erupting. Okay, now we're going to take a look at what disasters were caused by composite volcanoes. So this is the classic volcano horror story, basically. So in 79 AD, Mount Vesuvius erupted, and if you were watching the videos earlier on, you saw a bit about this. Everyone in the town of Pompeii was entombed in the pyroclastic flow that resulted from Vesuvius. So, taking a look at this, how would Vesuvius affect what is now Naples in Italy if a similar eruption were to occur? There are 3 million people that currently live in this area. And the famous eruption in 79 AD started with earthquakes, followed by the formation of an eruption column. So there were warning signs that were there, but the people at the time didn't know what to make of it. The tephra fall immediately followed by 6 pyroclastic flows, 3 of which hit Pompeii. So this was just a tremendous eruption. And if it were to occur now, again, 3 million people would be affected, not considering anyone in the surrounding area that would be affected by the ash carried by the wind. So it's it's a very serious situation when you have dense populations collecting around volcanoes, which is very common because the soil that is created as a result of these volcanic eruptions is fantastic for farming. So it's very common to have large populations near volcanoes, regardless of how dangerous that is. Our next example is Mount St. Helens. So taking a look at this, I want you to observe the geology of Mount St. Helens, comparing the cross-section on the bottom to the actual mountain. And this image is prior to the 1980 eruption. So the observations that I hope you will make is that there is a central vent, and there are layers of lava flows, pyroclastic rocks, and mud flows. So if a volcano has had pyroclastic flows in the past, you can expect it to behave similarly in the future. So Mount St. Helens was mapped and studied prior to the eruption, so they knew ahead of time that this is the type of behavior that can be expected from Mount St. Helens. The eruptive history included all the rock types listed in the legend there: the dome and the conduit, the lava flows and dikes, the pyroclastic rocks and mud flows. They also recognized evidence for horizontal blasts of ash, so not just shooting out of the top, but erupting out of the side. And then in March 1980, earthquakes were measured there, caused by magma moving around below the surface. And then in April 1980, there was a bulge that formed on the north side of the mountain. producing an unstable slope. By May 18th, 1980, there was another earthquake that triggered an avalanche of this bulge. The whole bulge slid right off of the north side, which greatly decreased the pressure within the volcano, and that lower pressure caused a lateral blast of magma. And this image on the right shows that a later, smaller eruption with a pyroclastic flow. Okay, so basically, we knew that this had happened in the past. We knew that it was a possibility, and now we know the warning signs because it will occur in the future, and it has been. Mount St. Helens has been active since that big eruption in 1980, so it makes sense that this will happen again. There's no way we can prevent it. All we can do is learn to monitor it as closely as possible and read the signs that it's telling us so we can get out of its way.